Up to this point, all chemical compounds we have encountered seem two-dimensional. However, most often than not, organic chemistry problems will require skill and imagination. There is no way out of this. We need to learn to see molecules in 3 dimensions. Stereoisomerism is a form of isomerism in which molecules have the same molecular formula and sequence of bonded atoms, but differ in the 3-dimensional orientations of their atoms in space. Molecules having such configurations are said to be chiral. The term chiral is derived from the ancient Greek word for hand, the canonical example of chirality. A right-handed configuration is denoted by the letter R. A left-handed configuration is denoted by the letter S. The R stands for the Latin word ictus, while the S stands for the Latin word inister. Humans are made of left-handed amino acids exclusively. The configuration is assigned following a set of rules, and the inister configuration of the building blocks of life does not in any way imply that all humans are evil. Before introducing stereochemistry, we need to know about stereogenic centers. Chiral molecules usually contain at least one sp3 carbon atom with 4 non-identical substituents. Such a carbon atom is called a stereogenic or chiral center. Any molecule that contains a chiral center will be chiral, with the exception of a meso compound, with molecular representations having increasing levels of abstraction. It is not always easy to spot a chiral center. Can you spot the chiral centers in the structure at the left? If not, you are not alone. We said chiral centers had to be sp3 carbons. Probably you were looking for a tetrahedral pattern. Nothing here looks like a tetrahedron, because the hydrogens are not shown. Just remember that carbon has 4 bonds. If you see only 3 bonds, then there is 1 hydrogen that is not shown. If you see only 2 bonds, then there are 2 hydrogens that are not shown. Now that we know about the incognito hydrogens, it is easier to see why the carbon marked with an asterisk is a chiral center. This is an sp3 carbon with 4 non-identical substituents: chlorine, isopropyl, 3-methylpentyl, and hydrogen. Because this structural representation does not show solid or hashed wedges, there is no way for us to assign a stereochemical label. It should be noted, the substituents chlorine, isopropyl, 3-methylpentyl, and hydrogen are listed in order of decreasing priority using the Can-Ingold Prelog system. As we will see in a moment, this ranking system is an integral part in the process of assigning stereochemical labels. How can we tell if an atom is not a chiral center? Simply look for mirror planes of symmetry. If an atom has an internal mirror plane of symmetry going through it, the atom is not a chiral center. An internal mirror plane of symmetry is a plane that cuts a molecule in half, yielding 2 halves that are mirror reflections of each other. For example, 2 identical substituents in an sp3 carbon create a mirror plane of symmetry, with 1 identical substituent on each side of the mirror plane. An sp2 carbon cannot be a chiral center either, because the trigonoplanar structure of an sp2 carbon has a mirror plane of symmetry. Let's look at some examples on finding chiral centers. Here we have a carboxylic acid derivative. Carbon number 1 is not a chiral center, because the carbonyl carbon has an sp2 configuration. Carbons 2, 4, and 5 are not chiral centers. These carbons are sp3, but 2 of the substituents are identical. Remember, there are 2 hydrogens at each bend of the carbon chain. Carbon number 3 is chiral. This carbon is sp3 and it has 4 non-identical substituents, listed here in order of decreasing rank. Here we have an amino acid. Carbon number 1 is not chiral, because it is an sp2 carbon. Carbon number 2 is chiral. This carbon is sp3 and it has 4 non-identical substituents, listed here in order of decreasing rank. Carbon number 3 is chiral. This carbon is sp3 and it has 4 non-identical substituents, listed here in order of decreasing rank. Here we have ibuprofen. Carbon number 1 is not chiral, because it is an sp2 carbon. Carbon number 2 is chiral. This carbon is sp3 and it has 4 non-identical substituents, listed here in order of decreasing rank. Carbon number 3 is not chiral. This carbon is sp3 but 3 of the substituents are hydrogen. Carbon X is not chiral. This carbon is sp3 but 3 of the substituents are hydrogen. Carbon Y is not chiral. This carbon is sp3 but 2 of the substituents are methyl groups. Carbon Cid is not chiral. This carbon is sp3 but 2 of the substituents are hydrogen. None of the carbons in the benzene ring can be chiral, because none of the carbons is sp3. The Canning-Gold Prelog rules assign priorities to the groups directly bonded to the chiral carbon. Having ranked the 4 groups attached to a chiral carbon, we describe the stereochemical configuration around the carbon by orienting the molecule so that the group with the lowest ranking is given a dash bond to indicate it points directly away from the viewer. If a curved arrow drawn from the highest to second highest to third highest rank substituent is clockwise, we say that the chiral center has the ictus configuration. If a curved arrow from the highest to second highest to third highest rank substituent is counterclockwise, we say that the chiral center has the inister configuration. In order to determine whether the chiral center is in the R or S configuration, there are a series of steps to follow. 1. Identify the chiral center as having 4 unique substituents. 2. Assign ranks based on Canning-Gold Prelog rules. 3. Rotate the molecule so that the rank 4 atom is behind the chiral center. 4. Determine if the ranking sequence rotates to the left or the right. For example, for R3-methylhexane, we place rank 4 hydrogen behind the chiral center. In the first round of elimination, all atoms attached to the chiral center are carbon. At this point we have a tie. In the second round of elimination, the methyl group gets rank 3, because the next bound atoms are all hydrogens, while the other 2 groups remain equally matched, having 1 carbon bound to each. In the third round of elimination, the ethyl group gets rank 2, because the next bound atoms are all hydrogens, while the remaining group has a carbon bound to it. This last group gets rank 1. For our 1,2-deuteriopropyl alcohol, we place rank 4 hydrogen behind the chiral center. Deuterium gets rank 3, 1 rank above hydrogen, because deuterium is the heavier of the 2 isotopes. Then we move on to rank the other 2 groups by comparing carbon and oxygen. The smaller atomic number of these 2 is carbon, with atomic number 6 for carbon. The ethyl group gets rank 2, with atomic number 8 for oxygen. The hydroxy group gets rank 1. For S-sec-butyl alcohol, we place rank 4 hydrogen behind the chiral center, with atomic number 8 for oxygen. The hydroxy group gets rank 1. Then we move on to rank the other 2 groups. By comparing carbon to carbon, we have a tie. In the second round of elimination, the methyl group gets rank 3, because the next bound atoms are all hydrogens, while the remaining group has a carbon bound to it. This last group gets rank 2. The process can be simplified further by hiding the lowest ranking group behind the chiral center, and showing only groups 1, 2, and 3. For example, consider the compound 1-bromoethanol. First we rank the groups using the Canning-Gold Prelog sequence. Bromine with atomic number 35 gets rank 1, because it has the largest atomic number of all atoms bound to the chiral center, with atomic number 8 for oxygen. The hydroxy group gets rank 2, with atomic number 6 for carbon. The methyl group gets rank 3, with atomic number 1. Hydrogen gets rank 4. Then we rotate the molecule so that the lowest ranking group is hidden behind the chiral center. Because the hydrogen was originally pointing towards the viewer, pointing the hydrogen away from the viewer brings the bromine to the front and apparently changes the order on which hydroxy and methyl groups are arranged. But the configuration of substituents 1, 2, and 3 does not change when moving our point of view down the bond of substituent 4. The curved arrow from the highest to second highest to third highest rank substituent is counterclockwise. The chiral center has the S configuration. The compound name is S1-bromoethanol. For the compound 2-butanol, we place rank 4 hydrogen behind the chiral center. With atomic number 8 for oxygen, the hydroxy group gets rank 1. Then we move on to rank the other 2 groups. By comparing carbon to carbon, we have a tie. In the second round of elimination, the methyl group gets rank 3, because the next bound atoms are all hydrogens, while the remaining group has a carbon bound to it. This last group gets rank 2. The curved arrow from the highest to second highest to third highest rank substituent is clockwise. The chiral center has the R configuration. The compound name is R2-butanol. Systematic Iupac naming rules must still be followed. This is particularly important when the structures become more complex. For example, according to Iupac ranking, the highest priority functional group in ibuprofen is a carboxylic acid. This determines the parent name of the compound, which is propanoic acid. The rest of the molecule must be named as a substituent. In this case, we have a benzene ring with an alkyl group at position 4. The alkyl group is 2-methylpropyl. The substituent is then named 2-methylpropylphenyl. The Iupac name for ibuprofen is then 2, open parenthesis, 4, open parenthesis, 2-methylpropyl, close parenthesis, phenyl, close parenthesis, propanoic acid. Because the ibuprofen from the pharmacy is a racemic mixture, the compound can be labeled as RS. Only the S configuration can act as an inhibitor for the enzyme cyclooxygenase and relieve pain. Because the active site where ibuprofen binds cyclooxygenase is chiral, the R configuration does not fit. The S configuration can be drawn by hiding group rank 4 behind the chiral center, then placing the substituents with ranks decreasing counterclockwise. The R configuration is the mirror image of the S configuration, and can be drawn by hiding group rank 4 behind the chiral center, then placing the substituents with ranks decreasing clockwise. In the previous example, 2 ibuprofen configurations were drawn by inverting the configuration of the chiral center. R ibuprofen and S ibuprofen are enantiomers. These are pairs of stereoisomers which are mirror images of each other. The R or S configuration is added as a prefix to a chiral molecule name to indicate which enantiomer is being discussed. Enantiomers have identical physical properties. However, enantiomers do differ in how they interact with polarized light, and they may also interact in very different ways with other chiral molecules. As we mentioned before, only the S configuration of ibuprofen fits the receptor sites on the enzyme cyclooxygenase and relieve pain. The R configuration does not function because the chirality of the molecule does not match the chirality of the receptor. The word enantiomer is very similar to the word twin, which is one of 2 offspring born at the same birth. The word is meaningless unless used in this context. You cannot have only one, and you cannot have 3. There must be 2 of them. If there are 3 of them, then they are not twins. Enantiomers also come in pairs. Each one is the non-superimposable mirror image of the other. If you have 3 stereoisomers, then they are not all enantiomers. One of them is probably a stereomer. To understand stereoisomers, it is necessary to think 3-dimensionally, and to consider the orientation or configuration of the atoms and groups in space. As the number of chiral centers increases, the number of stereoisomers for a compound increases rapidly, and orienting the lowest ranking group so it hides behind the chiral center is no longer efficient. As we already know, chemists use a solid wedge to indicate a substituent is projecting out towards the viewer, and a hashed wedge to indicate a substituent is receding away from the viewer. To draw the enantiomer of a chiral compound, keep the carbon skeleton the same, and reverse the solid and dashed wedge bonds on the chiral carbon. Doing this will invert the configuration of the chiral carbon. If the configuration inversion places the substituent rank 4 pointing towards the viewer, then you need to imagine you are behind the screen and your line of sight goes right through the bond of substituent 4. If you were to look from the other direction, the configuration you get would be incorrect. Here we have an enantiomer pair. Because it is not always efficient to rotate the molecule for viewing, you will need to use your imagination. You should pause the video if you still have trouble seeing the configurations of these two enantiomers. For molecules with multiple chiral centers, each carbon number is included before the RS configuration label. The stereoisomers can be easily drawn using solid wedge and hashed wedge representation. Here we have a set of stereoisomers. The representation is very basic, and the three-dimensional orientation of substituent rank 4 is enough to assign configuration. We start with the two chiral centers having the R configuration. Then we invert the configuration of one chiral center at the time to generate the other stereoisomers. The total number of stereoisomers is 4. The maximum number of possible stereoisomers that a molecule can have is 2 to the n, where n is the number of chiral centers. As the number of chiral centers increases, the number of possible stereoisomers for that compound increases rapidly. A molecule with 3 chiral centers can have up to 8 possible stereoisomers. Because enantiomers come in pairs, and each one is the non-superimposable mirror image of the other, the compound 2-chlorohexane-3-L, with 2 chiral centers, has 2 pairs of enantiomers. The matching enantiomer in the set is the one where the matching chiral centers have the inverse configuration. For example, the stereoisomer with configurations 2R, 3R, is the enantiomer of the stereoisomer with configurations 2S, 3S, and the stereoisomer with configurations 2R, 3S, is the enantiomer of the stereoisomer with configurations 2S, 3R. Any other combination of configurations are classified as diastereomers. We previously found 2 chiral centers for the amino acid threonine. The Iupac name for this compound is 2-amino-3-hydroxybutanoic acid. With 2 chiral centers, this compound can have a maximum of 4 stereoisomers. Here they are drawn using a more detailed version of the solid wedge and hashed wedge representation. The naturally occurring stereoisomer is 2S, 3R, 2-amino-3-hydroxybutanoic acid. Its enantiomer has matching chiral centers with their configurations inverted relative to the naturally occurring stereoisomer. This stereoisomer is 2R, 3S, 2-amino-3-hydroxybutanoic acid. We mentioned previously, the enantiomers differ in how they interact with polarized light. Light waves are oscillating electric and magnetic fields, randomly oriented in an infinite number of planes. When ordinary light is passed through a nickel prism, all planes of oscillation are filtered out except one, resulting in plain polarized light. Asymmetric molecules generate asymmetric electric fields, which interact with the electric field of the plane polarized light to induce its rotation. If a sample is 50% R enantiomer and 50% S enantiomer, the net rotation would be 0 degrees, because the rotation induced by the R enantiomer is countered by the rotation induced by the S enantiomer. If one of the two enantiomers is isolated, then there are no compensating mirror image molecules to counter the rotation of the plane of polarization. A compound that rotates plane polarized light clockwise is called distrorotatory. A compound that rotates plane polarized light counterclockwise is called levorotatory. The magnitude of the observed optical activity is dependent on temperature, the wavelength of light used, solvent, concentration of the chiral sample, and the optical path of the sample tube. This is why there is a defined set of standard parameters for optical activity measurements. Temperature, 20 degrees Celsius. Wavelength, 589 nanometers. Optical path, 1 decimeter. Concentration, 1 gram per milliliter. The specific rotation with such parameters is labeled as alpha 20D. For example, consider a generic enantiomer pair, R enantiomer and S enantiomer. In an experimental measurement, the R enantiomer rotates polarized light to the left, and the S enantiomer rotates polarized light to the right. This means a solution of R enantiomer, with concentration 1 gram per milliliter, at temperature 20 degrees Celsius, in a cell of optical path 10 centimeters, will rotate 589 nanometer polarized light by 25 degrees to the left. Warning: things just got complicated again. What are the odds? We have introduced the RS configuration assignment for enantiomers. If a curved arrow drawn from the highest to second highest to third highest rank substituent is clockwise, we say that the chiral center has the R configuration. If a curved arrow from the highest to second highest to third highest rank substituent is counterclockwise, we say that the chiral center has the S configuration. Then we introduced the DL assignment based on the direction plane polarized light rotates when interacting with each compound in an enantiomer pair. A compound that rotates plane polarized light clockwise is called distrorotatory. A compound that rotates plane polarized light counterclockwise is called levorotatory. It is very important to note that you cannot assign distrorotatory and levorotatory labels the way you assign RS configurations. The distrorotatory and levorotatory assignments are experimentally determined parameters. There is no simple way to know if an enantiomer is D or L until the direction of rotation of the plane of polarization is observed. Optical rotation can be used to quantify how much of one enantiomer you have relative to the other. Consider a mixture that contains 80% R enantiomer and 20% S enantiomer. The R enantiomer is said to be in excess. In order to quantify this excess, the term enantiomeric excess is used. It is easier to see how this works if we draw a rectangle representing 100% of the compound. Then color the 20% blue for the S enantiomer and 80% red for the R enantiomer. The 20% blue will cancel 20% from the red region. Think of this as a pseudo-racemic mixture inside the real mixture. As a result, only 60% of the compound total will contribute to the observed optical rotation. This can be expressed in a simple calculation that gives the enantiomeric excess using basic algebra. Consider the generic enantiomer pair we mentioned earlier. The R enantiomer has an specific rotation of 25 degrees to the left, and the S enantiomer has an specific rotation of 25 degrees to the right. If a mixture of both enantiomers rotates plane polarized light 18 degrees to the right, this means the S enantiomer is in excess. In order to quantify this excess, we take the ratio of observed to specific rotation and express the number as a percent. We obtain an answer of 72%. But this is not the final answer. The rotation of plane polarized light only detects the enantiomeric excess, not the enantiomeric amount. To obtain the enantiomeric amount, we add the part that did not induce rotation of the light because there was an enantiomer counterpart cancelling it. The final answer is 72% plus 1/2 of 28%. This means the mixture is 86% S enantiomer and 14% R enantiomer. The same calculation can be used for rotation of polarized light in the opposite sense. Chiral centers will not always confer optical activity. For example, A meso compound or mesoisomer is a non-optically active member of a set of stereoisomers, at least two of which are optically active. In order to understand what a meso compound is, consider the picture on the left. The girl's left and right hands are chiral. The term itself is derived from the ancient Greek word for hand, the canonical example of chirality. The girl's hair buns, ears, and feet are also chiral. However, the girl's body is not chiral. The reason for that is, the body contains an internal mirror plane of symmetry. Meso compounds are symmetric compounds that also have an internal mirror plane, so that the left and right side of the plane are mirror images of each other. Another characteristic of meso compounds is that they need to have at least two chiral centers. For example, 2,3-dichlorobutane is superimposable on its own mirror image, because it has an internal mirror plane. An internal mirror plane of symmetry is a plane that cuts a molecule in half, yielding two halves that are mirror reflections of each other. The mirror plane can cut through atoms and bonds. You need to be able to spot planes of symmetry in molecules so you can determine whether a molecule with chiral centers will be chiral or meso. A meso compound has two or more chiral centers and can be identified as meso because the configuration of the chiral centers is reversed across the plane of symmetry. It is easier to see the pattern in dimethylcyclopentane. Structures 1 and 2 are the same molecular structure. There is a mirror plane of symmetry halfway between the two methyl groups. Structures 3 and 4 are enantiomers, because reversing the configuration of the two chiral centers results in two structures that are the non-superimposable mirror images of each other. The Iupac nomenclature system is a set of logical rules devised and used by organic chemists to circumvent problems caused by arbitrary nomenclature. Now you know these rules, and given a structural formula, you should be able to write a unique name for every distinct compound. For example, consider what Juliet was asking. What is in a name? That which we call the rose by any other name would smell as sweet. Juliet was obviously referring to the chemical compound that gives roses their distinct smell. The most biologically active stereoisomer is levorotatory, but you would not know that from looking at the structure. We start by determining the parent name of the compound. This compound has a 6-carbon ring, like cyclohexane but with one carbon replaced by an oxygen. The preferred Iupac name for this ring structure is oxane. There are two chiral centers in the ring structure. Because the number 1 in the ring gets assigned to the oxygen atom, the chiral center assignments are carbon 2 and carbon 4. The substituent at carbon 2 is 2-methyl-1-propanol. The substituent at carbon 4 is methyl. The Iupac name without stereochemical configuration is 4-methyl-2, open parenthesis, 2-methyl-1-propanol, close parenthesis, oxane. Up to this point, the Iupac priority ranking has determined the parent name and suffixes. Now we just need the stereochemical configuration. The top right image has the rank for our groups pointing towards us. You can read the correct configuration if you imagine you are on a space inside the screen. But the bottom right image has the right configuration for stereochemistry viewing, so we don't need to go through all that trouble. For chiral carbon 2, group ranking decreases counterclockwise. This is the S configuration. For chiral carbon 4, group ranking decreases clockwise. This is the R configuration. And because this enantiomer rotates plane polarized light counterclockwise, we add a minus sign to the name. The Iupac name including absolute configuration is -2s4r 4-methyl-2, open parenthesis, 2-methyl-1-propanol, close parenthesis, oxane.